So in previous lecture, we learned about a brief overview on the computer vision field, and also we reviewed how to use the OpenCV library. Okay, so we already uploaded the lecture video in the Blackboard, right? So you can confirm that in the Blackboard. Okay, and also we uploaded the Colab notebook file whose format is IPYNB, and you can upload that file to your Colab environment. Then you can actually load it, right? So the material in previous class have some code, right? You don't have to type all, but if you upload that notebook file in your Colab, then you can load all the code automatically, okay? So it will make you convenient, okay? And I recommend you to practice the OpenCV, okay? Because it's kind of essential things. Okay? 지금 성함 뭐죠? 들어오신 분? 주형? 이주형? 알겠어. Okay. So today we will learn about deep learning. So I'm assuming that most of you are familiar with this, but I'm just reviewing this deep learning, okay? So I already explained this slide in previous lecture, but this is kind of the largest scale challenge in image classification task, okay? So image classification, this is task that categorize images according to their main object, okay? They are assuming that there is just one object in each image, right? And the task here is to classify images according to that main object, okay? So in this challenge, there are 1,000 classes, and they collected a large amount of data. So using the training data, they trained some CNN, convolutional neural network model, to classify 1,000 objects, okay? And then they use this test data to compete each other, okay? And I already explained this graph in previous lecture. So the x-axis is the year, right? And y-axis is the error rate. This is 1 minus accuracy, right? 100 minus accuracy, okay? So error rate should be minimized, okay? So in the year of 2010 and 2011, the best performed algorithms were based on the SVM, which is the shallow learning algorithm. But in the year of 2012, deep learning approach recorded as the state of the art. Okay, it best performed, and actually it exhibits 10% gain. Okay, so everyone here, every researchers who are doing this challenge are surprised. Okay, and after that, researchers are mostly use the deep learning architecture. They anymore not use the shallow learning method. Okay, and instead they try to stack more layers. So here they are using 8 layers, but gradually they use more and more layers. Okay, so this is the event where the deep learning approach getting how deep learning approach become popular in computer vision domain. And in the year of 2015, the ResNet architecture, which is the CNN, famous CNN network, appeared, and it has very large, very deep layers, right? Over 100 layers, and it surpasses the human performance in image classification task, okay? So these two events are very important in vision domain. After that, people are more and more involved in using the deep learning architectures, okay? So this slide is showing the conceptual difference between the deep learning architecture and the shallow learning architecture when dealing with the vision task. Okay, so this is the shallow learning method, and the bottom is the deep learning architectures. Okay, so we normally input images, right, to the some code, right, to the deep learning model or shallow learning model. We input the images, okay, and the computer represent the images as the array, okay. So normally, if the height, this is the height, and this is the width, and this is the channel number, okay. Width and height, you may be familiar with. But channel, we always have 3 channels if we are dealing with color image, okay? There are R, red, green, G, blue channels, okay? So there should be these 3 channels in color images, okay? And normally in CNN, their input size is around 2 to 4 by 2 to 4, okay? So if the image size is larger than this, we normally resize it using OpenCV, maybe, okay? So this is our input. And in shallow learning algorithms, this is the deep learning algorithms, we extract some features, the feature which captures some important characteristics of the object, okay, we are dealing with. So for example, let's say we are dealing with face detection task. The task is to detect the human faces from the images, okay? Let's say we are dealing with face detection task. Then the important feature might be the skin color, okay? So when detecting the human face, we have to detect some skin color or some textures of the pixels might be important, right? Anyways, we have to, by ourselves, think about which features are useful for that task, right? So we humans have to engineer which features might be important for each task, right? And we have to develop some feature extraction method by human engineering. And then when features are extracted, we input it to some shallow learning algorithm, such as SVM and logistic regression method and others, okay? So most of these shallow learning architectures are having just one layer, okay? They are just multiplying some parameter. Let's say this feature is some f. Let's say let's denote this feature vector as f. Then the thing we do in shallow learning algorithm is multiplying some weight to the feature vector and adding some bias. Okay, this is happened here, and we will get some output value. And if this is larger than some threshold, we will call it as +1 class. Or if this is less than -tau, maybe, then we will call that as -1 class. Okay, this is the logic happened here in previous shallow learning pipelines. Okay, but in deep learning method, as you see here, the yellow things are representing the layers. Okay. This is representing the multiplying W and adding bias, okay? They are representing this, okay? So we apply these operations multiple times in deep learning architecture, and then map it to some finite value, which may have some +1, some may have some and anyways value, and we threshold it or use it anyways for the multi-class classification or things. Okay. Anyways, the important thing is the shallow learning method. We by ourselves have to extract feature. We have to define by ourselves how to extract which feature, right? And if the task become different, for example, if we want to detect the cat, right, this time, then maybe this feature vector should be re-engineered, right, by ourselves. Okay. So every time the task is changed, we have to define human engineered features by ourselves. Okay. But in deep learning architecture, we don't have to do that. Okay. This architecture, in the early layers, it rules as the feature extractor, and in the later layer, it rules as the classifier. Okay, so by stacking multiple layers, it automatically rules as feature extractor and at the same time as the classifier. So we don't have to define the feature vectors by ourselves, okay? But it's optimally decided based on the data, okay? So this is the reason why deep learning approach performs better than the shallow learning approach, okay? So maybe if some people ask you why deep learning is better than shallow learning, then you can answer these too, maybe, okay? First is, we can extract the optimal representation, optimal feature vector via the end-to-end training using the data, okay? That's the merit of deep learning, okay? But in shallow learning, we have to define our own feature vector, okay? So maybe we humans can make mistake, right? Even for the face detection task, we can omit the color, skin color feature, right? In that case, the accuracy of the pipeline would be reduced, right? But in deep learning pipeline, we don't have to care about the feature vector, their configuration. So it automatically learns. So that's called as end-to-end learning, right? From input to output, end to end, it is trained based on the data. So we don't have to care about intermediate layers, how to configure intermediate layers. So it's more optimal, okay? And even the tasks are becoming different, we don't have to care. We just, if we just train new parameters for the deep learning architecture, it automatically learns, okay? So it's the good thing in deep learning architecture, and that's one reason why deep learning architecture performs better than the shallow learning method, okay? And the second one is nonlinearity. So this is mathematically proven that if you use just one layer, that does this operation. It is kind of linear. It is doing the linear mapping between input and y, output y. So let's say this is the input x, and this is the output y. Then this is the linear equation. So their graph looks like this, right? Their output need to have some linear relationship with the input vector. Okay, so this type of formula only can represent when the input and output have the linear relationship. Okay, let's say this is height, and this is the weight. Okay, we are given height and weight data for maybe 100 persons, okay? And we want to train our model using that data and want to estimate weight from unknown person's height, okay? That's kind of machine learning problem, okay? So given many weight and height data, we will train our model, and using that trained model, for unknown person's height, we want to estimate their weight, okay? That's the typical machine learning problem, right? In that case, if we use this linear model, using just one layer of the classifier, then when this data, weight and height, are having the linear relationship, then the accuracy of the classifier will be good. But if, let's say, this X and Y are highly nonlinear case, like this X is image, let's say this X is, how to say, some maybe number of humans inside the image, let's say, that's somehow correlated, but it's hard to map from the image pixels to the number of humans directly, okay? So that's kind of nonlinear mapping things, okay? In that case, this linear operation might be limited in their performance, okay? So we need to have the classifier which can represent the nonlinear relationships in the input and output domain, okay? But the simple things we can do is, if we stack multiple layers, it is mathematically proven that there becomes to have the nonlinearity, okay? If we stack multiple layers, then it tend to represent the nonlinear mapping, but not always. But it can have some possibility of representing the nonlinearity. Okay. So, and also most of the real world data, real world problems, they are nonlinear. They requires nonlinear mapping, right? So there's not much problem that requires only the linear mapping, okay? So because of that, deep learning can represent the nonlinear relationship better than the shallow learning methods. And at the same time, in the real world, most of data requires the nonlinear mappings. So that's why deep learning approaches are maybe performs better than shallow learning in real world data. Okay, this is two reasons why deep learning is preferred compared to the shallow learning method. Okay, so if someone asks you why deep learning is better, then you can answer like this. Okay, so this CNN is the not first, but was the very popular deep learning architecture that was proposed in here. Okay, in before 2000, there are some other deep learning architectures that stacks multiple layers. Okay, if we stack multiple layers, it is called as deep learning, right? But this CNN was the first successful architecture that performs good in image classification task, right? So this CNN is most popular, right? But nowadays, another architectures like transformer and other things are gradually coming, and it is replacing this CNN. But anyways, this CNN was very popular deep learning architecture. Okay. So now we will learn about this CNN. Okay. It is the convolutional neural network. Okay. So neural network is kind of the name which is similar to deep learning. Okay. But most distinct distinct part of the name is convolutional. Okay. So convolution operation, maybe you may learn about this convolution operation in signal processing class in undergraduate course, right? Maybe if you are majoring in electrical engineering or other related major, then you may heard about the convolution operation before. Okay. Even though you didn't heard about this, there's no problem, right? Okay. This convolution operation is a useful operation for processing the signals. Okay. Most of filters we are using in maybe Photoshop, this convolution operation is used. So roughly, you can think applying the filter is same as applying the convolution operation, right? So convolution is roughly equivalent to the filtering operation. Okay? If you want to apply some sharpening effect in Photoshop, you are applying some convolution operation with the sharp filter. And also, if you want to apply some blurring effect on your photo, then that's actually applying some blurring, some convolution operation with the blurry filter, right? So filtering is actually equivalent, roughly equivalent to applying the convolution operation, okay? Okay. But I mean, this convolution is not maybe the optimal operation for constituting this deep learning architecture. But it is very useful operation for processing the signals, like 1D signals like the speech, or 2D signals like the image. Okay. So previously in image processing domain or signal processing domain, this convolution operation was widely used already. And because we are dealing with images, okay, for the image classification task, we are dealing with the images, okay. So some people think to constitute the deep layers with this convolution operation, okay. That's actually the CNN architecture, okay. Nobody can maybe prove this convolution operation is best, okay. But in practice, it performs very well. Okay, so people are widely using that. Okay. More important thing is when stacking this deep architecture is all of the components in the deep architecture should be differentiable. Okay. So why is this differentiable means it has to be the output needs to be differentiable respect to input, first input and their parameters. Okay. So I will remind you this again later. Okay. So any layers in between these that constitute the deep architecture have to meet this condition. Okay. And this convolution operation is meeting this condition. And at the same time, they are widely used in processing image signal. Okay? So they were adopted in this CNN architecture, and it performs well. So people are using that. Okay, that's the story, right? So in this deep learning, using this fully differentiable deep layers, we input our RGB image and then map it to some vector which represents some probability for multiple classes. Okay, so using the data, we learn the parameters of these deep layers. Okay, and these deep layers could be trainable when they are differentiable to when their output is differentiable with respect to their input and their parameters. Okay. Okay. So all are following this. Any questions? Okay. Okay. And let's say this is the overall deep architecture. Okay. And it needs to be differentiable. Okay. Their final output needs to be differentiable with respect to their input, the initial input, and at the same time, the final output should be differentiable with respect to their whole parameters. Okay. And if the whole pipeline is differentiable, then by the chain rule, I mentioned that let's say the final output is L, and the initial input is I, and let's say the intermediate parameters are theta, right? Then we can, if the entire architecture is differentiable, then it means we can get these two, right? So the final output should be differentiable with respect to its initial input, okay? This is the first thing, right? And the final output should be differentiable with respect to their intermediate parameters, okay? That's the second thing, right? Okay. And by the chain rule, this could be divided, separated into multiple terms. Okay, let's say they are composed of 3 layers here, right? So these 3 components are all differentiable, and they are constituting the overall entire architecture, right? In that case, this DLDI could be divided like this. Right? This is the chain rule, right? And also DLD sector, but let's say this is sector 1, let's say this is sector 2, and this is sector 3, right? Let's say it like that. So sector 1 is layer H's parameter. Sector 2 is layer F's parameter. Let's say this is the layer G's parameter, right? Let's name it like this. Then let's say if we want to find this DLD sector 1, then this could be divided like this. Right? Are you following this? Okay. So anyways, we can, if the entire network is differentiable with respect to their input and their intermediate parameters, they can be separated like this, okay? And then this is meaning that each individual layers that constitute the entire differentiable layer have to be differentiable to their input and their parameters, right? Okay, so I mean, for this layer H, to obtain if these two terms exist, then these two terms need to be valid for this layer H. right? And also this term and dy d sector 2 have to be valid for this f, right? And this term and dy d sector 3 have to be valid for this layer G, okay? Right? So conversely saying, I mean, if individual layers that constitute the entire layer is differentiable to its input, and at the same time they are differentiable with respect to their parameters, then the entire network becomes differentiable with respect to their initial input and their intermediate parameters, okay? Are you following this? This is very important, okay? And the thing why we have to do this is we want to do this. Okay? I mean the input and output, and this is the deep learning architecture, right? Which is differentiable, right? And let's say their parameter is sector, right? We normally randomly initialize these parameters, right? At the initial stage. Then if we input some input image to the network, then their output is some random value, okay? It totally doesn't work, right? But by supplying some training data and by updating this sector value, it gradually become working as we intended, okay? So this is the rule for updating this parameter sector, right? Our parameter should be updated during the training stage, right? It is initially random, but it has to be trained, right? And this rule is, this is old value, and this is new value, and we subtract something to the old value and make some new parameter, right? This is iteratively updating the parameters, right? And here you can see there's some value like this, right? DL sector, right? This L is kind of loss function. It measures the distance between the ground truth and our final prediction, right? If at the initial stage, our final value is totally random, and it will be different, far different from the ground truth, right? So the loss is high at the initial stage, but maybe if the training goes, the loss will be reduced, right? Anyways, the term, this loss function is defined, is also differentiable. So anyways, we can think this Y is the final prediction from the deep learning architecture, and this layer G is also the loss term. And let's say this loss L is the final value. We can think like that. Strange. Okay, sorry, I'm not sure why it happens. Okay, so anyways, the mapping to final prediction to loss L is also differentiable. You can interpret it as the differentiable layer as well, right? So the final output, the gradient by the differentiable, anyway, this term, the differentiation of final output y respect to the parameters, and then you can multiply some loss layer, and then you can get this DL sector, right? So anyways, this term is representing how much the loss function is, the distance between final prediction and ground truth is changed according to our parameters. Okay? This gradient term, you already know this, right? You may learn about this in high school, right? Gradient. Okay. This is representing some, this is representing how much y is varied according to x changes, right? So dl d theta, it is meaning how much our loss function is changed depending on our parameters, okay? And this minus is the direction towards minimizing the loss function, okay? So this term is actually gradually minimizing our loss function. And for that direction, we are updating our parameter sector, okay? And this could be obtained when entire layers are differentiable, right? And entire network becomes differentiable when individual layers are differentiable, right? Okay. That's the important concept here, right? And this convolution is the operation widely used in image processing domain, but it's differentiable, right? So people use this convolution for the image classification field, right? And it works good, okay? So it becomes popular, right? Okay. And the thing is, if we constitute the layers, deep layers, using this kind of operations, plus, minus, multiplication, and division, then their output, if we constitute the input using these four operations, then always mostly always, the output becomes differentiable respect to their input, okay? And the convolution operation, maybe some of you already know about that. They are composed of mainly these two operations, right? So their output is differentiable to their input, okay? So that's the thing. Okay. And okay, and this is the maybe last part in today's lecture. And I will explain how in computer they are calculating the gradient. Okay, so in the deep layers. Okay, so let's say this is the three input variables. Okay, and we first add this x and y. Okay, and then we multiply their output with z and find the final output. Okay, so if we write it in formula, then it could be like this, right? Okay. Right. This graph is representing this formula, right? And so this is forward path. I mean, how we calculate the output from the input. That's called as forward process. Okay. But we have to define how to get these three gradients. Okay. And we call this as the backward process. Okay. So forward process, we normally process from left to right, right? But in backward, we have to somehow process the things from right to left, right? So it's called as backward process, okay? So given these things, I will show you how computer calculate these three gradient. Okay. Okay, and let's say we need some initial values for these three variables. And let's say x is initialized to -2, y is initialized to 5, z is initialized to -4. Okay. Then if we add these two, then their output is 3, right? And then we will multiply these two, and the final output might be -12. Okay. So this is easy, right? Okay. But in the backward process, it is not that simple, even for humans, right? But we can calculate it step-by-step manner. And we will initialize this last node's gradient as 1, because it is df, right? If we differentiate the last node respect to itself, then it would be 1. Okay, so this is gradient 1. And then we have to find df dq. Okay, this is kind of, let's say this is the layer. We can interpret this as layer, and this is differentiation of this layer's output respect to their input, its input, right? So their output for this layer, its output is f, and its input is q. Okay. So df dq is the differentiation of this layer's output respect to its input. Okay. And actually, when calculating this df dq, we need the original equation like this. Okay. And when we calculate, when we differentiate this equation respect to dq, z becomes constant. We can interpret z as constant, right? And it has -4 now, right? This is -4. It's initialized to -4, right? So this is equivalent to applying this to this, okay? And again, now we can apply this to each side, and we can get this, okay? So df dq is -4, right? Okay, so we can write it like this, okay? And at the same time, for this node, we have to calculate df dz, okay? Again, the same rule could go here. And this time we will apply d dg, right? Okay. And we can interpret q as constant this time. Okay. And that was actually 3, right? So, and then if we apply this to two sides, we can get df dz is 3. Okay. So here we can write it as 3. Okay. And then we then have to calculate df dx and df dy. We already calculate df dz because it's the it is constituted with one layer. It's simple, right? But for calculating these two, it is constituted with 2 layers, right? And we already get gradient for this later layer, okay? Then df dx could be calculated by two steps. Okay, right? By these two steps, we can calculate df dx. And for this, we already calculated as -4, right? The thing we have to further calculate is dq dx, right? And that is the relationship between q and x. And actually, they were having this relation, right? And for calculating dq dx, y can be regarded as constant, right? And it is initialized as 5, right? And we can apply dq for dx for two terms. So it results in 1, okay, right? So this is constant. So if we apply this, then this goes 0, right? And if we apply dx to x, then it becomes 1, right? So dq dx is now 1. This is 1, and this is -4. So df dx is -4, right? So this value. And again, for y, this is composed of two steps, dq dy, dq df, sorry. And we already calculate this as -4, and we have to calculate this. And using the same formula, 2, and by applying d dy to two terms, we can get it as 1. So this is 1 -4. So the entire term have the -4. Okay. I mean, you can practice this by yourself. Okay. Normally, I raise this as the quiz problem. So I recommend you to be familiar with this. Okay. So we are uploading the video, right? So you can follow the steps maybe using the video. Okay. So this is the method in a computer how they calculate the gradient in deep layers. Okay. Even for deep layers, we can step by step calculate the gradient. Okay. So it is almost time. So and then this is the kind of generic deep learning architecture, but CNN was the best performed CNN architectures, right? So we will then learn about what the exact layers that is constituting the CNN network later. But more important thing is most of the layers that constitute the CNNs are differentiable, okay? And we can learn them, okay? I mean, somehow we can reconfigure all the layers in the CNN network, right? As we want when constituting and when training the CNN, we can reconfigure all the layers, right? If the dimensions of the input and output, they are fit, then I mean, we can reconfigure every structure, right? That's why, I mean, because each individual operations in CNN, the convolution layer and pooling layer and some of the nonlinear layers are differentiable. Their output is differentiable with respect to their input, and their output is differentiable with respect to their parameters. They can be learned, right? So that's the reason. Okay, for that. Okay. So any questions? No? Okay. And yeah, let's finish today's lecture here. Okay, thank you. And see you this Wednesday. Okay, thank you.